The Caterpillar 797F, the biggest truck ever put to work. Somewhere in the high desert of northern Chile, at an altitude where the air is thin and the sun is brutal, a truck is climbing a road carved into the side of a mountain. It is carrying 363 metric tons. Its engine is producing more horsepower than a fleet of 40 sports cars combined. Its tires are taller than a grown man standing on another grown man's shoulders. And the driver sitting in the cab, a single human being drinking coffee from a thermos, is completely alone up there, higher off the ground than the roof of a two-story house, guiding this machine up a grade steep enough to make your palms sweat. This is not science fiction. This is not a concept vehicle. This is the Caterpillar 797F, and it is working right now, somewhere on this planet, doing something that should not be physically possible. Most people will never see one in person. They exist in a world that is deliberately hidden from ordinary life, behind security fences, inside restricted mine sites, in some of the most remote and inhospitable corners of the earth. But the products they help extract touch every single person alive. The copper in your phone, the iron in the car you drive, the coal that powered the city you live in. The 797F is one of the primary reasons the modern world exists, and almost nobody knows its name. That changes today. Why the world needed a truck this big? To understand the Caterpillar 797F, you first have to understand the world it was built for, and that world operates by a completely different set of rules than anything in ordinary human experience. Modern mining is not about tunnels and pickaxes. The largest mining operations on Earth are open-pit mines, massive terraced excavations that descend hundreds of meters into the Earth's crust, stretching 3 or 4 kilometers across. The Bingham Canyon mine in Utah is so large it can be seen from low Earth orbit with the naked eye. The Escondida copper mine in Chile produces so much copper that it meaningfully influences global commodity prices. They are industrial civilizations. And at the heart of every open-pit mine is a single brutal economic equation. The ore, the valuable material, sits mixed with enormous quantities of waste rock. To get to the ore, you have to move the waste. To move the waste, you need trucks. And the more waste each truck can carry per trip, the fewer trips are needed, lower fuel cost per ton, lower tire wear per ton, lower labor cost per ton. Every incremental increase in payload pays dividends. Mining companies understood this equation long before Caterpillar built the 797F. They had been pushing for decades to build bigger. The 797F was Caterpillar's answer, first introduced in 1998, then refined into the C variant, and finally the 797F in 2009. Each generation bigger, each generation more capable. Pushing further into territory engineers had previously declared impossible. But here's what nobody tells you. It's not just about moving material. It's about changing the fundamental economics of an entire industry. And the way it does that is more clever than most people realize. But that's not even the most incredible part. Because the real reason companies spend $5 million on a single truck goes far deeper than payload capacity. But first, the numbers. Numbers that should not be possible. Let's start with the tires. Because if you don't understand the tires, you don't understand anything about the 797F. Each tire on the Caterpillar 797F stands 4 meters tall, 4 meters. The average interior ceiling height of an American home is about 2.4 meters. The 797F's tires are taller than that ceiling by a significant margin. Stand next to one and it doesn't just tower over you, it makes you feel genuinely small. You are looking up at something that your brain refuses to categorize correctly, because your brain has no reference for a tire this large. Each tire weighs approximately 5,300 kilograms. That is heavier than a fully loaded Ford F-350 Super Duty pickup truck. Just the tire. Not the wheel it mounts on. Just the rubber. And each tire costs between $40,000 and $50,000 US. The 797F runs on 6 of them. Do the math, and you're looking at $250,000 in rubber. In the harsh, rock-strewn environment of an open-pit mine, those tires might last anywhere from 6,000 to 12,000 operating hours. Managing tire lifespan is a multi-million-dollar operation involving dedicated teams and sophisticated tracking systems. But that's not even the most incredible part. The operating weight, when fully loaded, reaches approximately 1,975 kilograms. A fleet of just 7 fully loaded 797F trucks would collectively outweigh the entire Eiffel Tower. Moving, on tires, across a gravel road in the Chilean desert. The payload capacity sits at 363 metric tons per load. That is 363,000 kilograms of ore in a single trip. A standard semi-truck is limited to 36,000 kilograms. The 797F, fully loaded, weighs roughly 28 times that. The engine that powers the impossible. Under the hood lives the Caterpillar C175-20 diesel engine, 20 cylinders, 106 liters of displacement. A typical sedan displaces around 2 liters. This engine displaces 106 liters. It is an industrial power plant mounted in a vehicle. This engine produces 4,000 gross horsepower. A Formula One car produces roughly 1,000 horsepower. The air filtration system is remarkable. The filters are the size of oil drums, removing fine silica dust from the mine environment. Caterpillar developed a cooling system so large it occupies a significant portion of the truck's front structure. The 797F could climb grades, in heat, at full load, that its predecessors simply could not manage. But that's not even the most impressive engineering story, because the braking system is something else entirely. A moving city of systems. The Caterpillar 797F is not a truck with some systems bolted onto it. It is an integrated machine in which every system affects every other system, and understanding how they interact is essential. Consider the braking challenge. A vehicle weighing 1,000,000 kilograms loaded with 363 tons of ore descending a steep mine ramp. The kinetic energy involved is staggering, far beyond what conventional brakes could absorb without catastrophic overheating within seconds. The 797F addresses this with a multi-stage braking strategy: engine compression braking, hydraulic retarding, and service brakes held in reserve. The retarder system alone can dissipate enormous amounts of kinetic energy, converting it to heat and rejecting it through a cooling circuit. Managing this system correctly on a long downhill haul is a core competency. Get it wrong, and you face a runaway vehicle. The retarder system doesn't just protect the brakes. It fundamentally changes how the truck can be operated, allowing for faster cycle times. The retarder is a productivity feature that also saves lives. Simultaneously, the hydraulic system controls steering and the massive bed hoist. It operates at pressures that would slice through steel. The hoist cylinders are among the largest hydraulic actuators in the world. When the bed raises to dump a full 363-ton load, those cylinders support a weight that most cranes could not lift. The dump cycle happens dozens of times per shift. The reliability demands on that hydraulic system are extraordinary. The electrical system runs on 24-volt DC architecture, powering Caterpillar's product-linked telematics system to transmit operational data continuously. Engineers thousands of miles away can see engine temperature, fuel consumption, and payload weight in real time. If something is trending toward failure, the system flags it. A single unplanned breakdown can cost hundreds of thousands of dollars. The cab, a world above the world. Accessing the cab is an experience that immediately reframes your understanding of scale. Access is via 3 flights of stairs. The climb passes engine covers, hydraulic reservoirs, and battery boxes. By the time you reach the cab door, you are standing higher than the roof of a standard single-story building. Once inside, the cab is sealed and pressurized. Outside, the C175-20 engine is loud. Inside, it is a manageable rumble. The climate systems handle extremes from 40 degrees in the Atacama Desert to -40 in Canada's oil sands. The operator's seat is designed to isolate the body from shock. Fatigue management is vital when controlling a machine of this power. The instrument cluster combines traditional gauges with multiple LCD screens displaying machine health data, camera feeds, payload information, and navigation. The payload monitoring system, integrated into the truck's suspension, tells the operator in real time how much material is in the bed. Overloading destroys tires and suspension components at rates that make it economically catastrophic. Underloading leaves productivity on the table. Getting the load right, every cycle, is part of the operator's job. Visibility forward is good by the standards of the machine's class. But the sheer width of the truck means the operator cannot see the ground near the front corners without the camera system. Reversing is done primarily on cameras and sensors. In many modern mining operations, the 797F is integrated into a site-wide traffic management system, using GPS to monitor every vehicle simultaneously and provide alerts when machines are on a potential collision course. Given that a 797F at operational speed cannot stop quickly, these systems are genuine accident prevention infrastructure. And this is only the beginning of what makes operating one of these machines so demanding. Because the real challenge isn't the machine itself, it's the environment it operates in. And what engineers discovered about that environment changed how mines are designed. A Caterpillar 797F does not roll off an assembly line the way a pickup truck does. The machine is too large to transport assembled. Major components are manufactured at Caterpillar's facilities and supplier plants globally, then shipped separately to the mine site. The frame sections are fabricated from high-strength steel alloys, welded to tolerances that ensure the structure can withstand millions of load cycles. The engine is assembled and tested as a complete unit before shipping. The axle assemblies are built and verified separately. At the mine site, a factory-trained assembly team works through a precise sequence over several weeks, bolting components into a complete machine. Every fluid system is flushed and filled. Every electrical connection is tested. Every hydraulic circuit is pressurized and checked. The engine runs through a break-in procedure before any load is applied. The commissioning process verifies the machine operates within specification. A new Caterpillar 797F costs approximately $5 million. Total investment per unit can approach $7 million with shipping and training. Most large operations run fleets of 10 to 30 machines simultaneously. The capital commitment is enormous, and yet mine operators make it without hesitation, because the productivity return justifies the investment. At full production, a single 797F generates more value per operating hour than almost anything else. The cost per ton of material moved is lower for the 797F than for any smaller truck. Bigger is genuinely cheaper at this scale. That is the economic reality that drives the ultra-class market. At the Escondida copper mine in Chile, fleets are the reason for its massive production. That copper flows into the global supply chain for electric motors, power cables, and the infrastructure of electric vehicles and renewable energy. Every electric car contains roughly 83 kilograms of copper. Every wind turbine contains tons of it. The global energy transition is copper-dependent, and the copper that makes it possible comes out of mines, moved by trucks like the 797F. The iron ore operations of Western Australia's Pilbara region tell a similar story. The Pilbara produces hundreds of millions of tons of iron ore per year, feeding steel mills across Asia that produce structural steel for buildings, bridges, ships, and infrastructure projects worldwide. Ultra-class haul trucks are the backbone of Pilbara haulage. Without them, production drops, steel supply tightens, construction costs rise. The economic ripple from a fleet of trucks in a remote Australian desert reaches every city on Earth. This is the hidden reality of the Caterpillar 797F. It does not appear in your daily life in any visible form. You will never see one on a road. You will never pass one at a traffic light. But the materials it moves are in your home, in your car, in the infrastructure of the city around you, and increasingly in the clean energy systems the world is building for the future. The 797F is invisible and indispensable simultaneously. And that combination, invisible, indispensable, operating at the absolute limit of what engineering can achieve, is what makes it one of the most remarkable machines, the boundary of what is possible. There is a physical limit to how large a wheeled haul truck can be. Engineers know where that limit is because they have mapped it from multiple directions simultaneously. The tires cannot be made larger than a certain point. The manufacturing equipment does not exist, and the rubber compound cannot maintain structural integrity. The haul roads cannot be made wider indefinitely. The earthworks cost becomes prohibitive. The axle loads cannot increase beyond certain thresholds. The Caterpillar 797F sits at that boundary. It has sat there for years. Competitors have reached similar boundaries. The Liebherr T282C, the Bell AZ757 TIL, the Komatsu 980E, each arrived at the same physical frontier. What the 797F represents, therefore, is not just the largest truck Caterpillar ever built. It represents the largest truck that the laws of physics permit. There is a moment that mine workers describe. It happens when a fully loaded 797F begins climbing a steep haul road. The engine note deepens. The transmission locks. This object, weighing nearly 1 million kilograms, carrying a load that would fill 3 swimming pools, begins to move. Not slowly, not laboriously. It moves with purpose and pace. It climbs. And watching it disappear, you understand something specification sheets cannot convey. Human engineering pushed to its absolute limit is extraordinary. The Caterpillar 797F is not just a truck. It is proof that when engineers are given a hard enough problem, the results defy ordinary imagination. Every smooth road, every copper wire, every steel beam. Somewhere in their history is a machine like this one, working in the dark. And we are just getting started. Next up, the machine that makes the roads the 797F drives on. A grader so precise it can shave a surface flat to within millimeters. A machine doing work the entire industry depends on every single day.